All right, welcome everybody. Today we're going to talk about section 6.3, and this is all about an introduction to something called a logarithmic function, or a logarithm for short. We've been talking about exponential growth and decay for the last couple of days, and that is something that you are very likely familiar with, either from Algebra 1 or even from middle school. This idea of a logarithm might be something that's brand new to you, not that it's difficult, but if it is brand new, you're going to want to take special care to make sure that you are doing the homework and asking questions on a timely basis. That way you don't fall behind. So in order to first introduce what a logarithm is, you first want to think about an exponential. So think about, for example, the fact that we know that 2 squared is equal to 4, and we know that 2 cubed is equal to 8. We've spent a lot of time in chapter 5 using the power rules and the exponent rules. So those are kind of things that we're familiar with. But what would happen if we tried to solve the equation 2 to the x equals 6? Well, we're not able to find that value in our heads. We know that it has to be between 2 and 3, because if 2 squared is equal to 4 and 2 cubed is equal to 8, we know it has to be somewhere between 2 and 3, but we don't want to just guess. We want to be able to find that number exactly. And in order to do that, we're going to use a logarithm. So the first thing you have to understand about a logarithm is how is it related to an exponential? And it turns out it's related in the following way here in the blue box. We would say log base b of y is equal to x if and only if b to the x equals y. So notice here, it's telling you below how you would say it in words. So again, the left-hand side, log base b of y, that's how you would say it. And basically what the statement means is that the left side is equivalent to the right side. Now, the if and only if part means that it could go both ways. You could start with the left side and turn it into an exponential, or you could start with the exponential side on the right and turn it into a log. And that's the very first thing that we're going to do below. There are lots of different ways that you could do this, but one of the most famous is something called the loop rule. So I'm going to show you how to use the loop rule, and if you find it helpful, you're going to use it as well. So let's start with the logarithmic side. If you wanted to take the log side, which again is over here, and if you wanted to turn it into the exponential side on the right, you're going to start at the base, you're going to draw a loop to the other side, and then you're going to come back. And if you go ahead and write your exponential using the loop, start with the b, raised to the x equals y. That's how you use the loop rule to get from the log side to the exponential side. Let's say you wanted to go the other way, so you want to start with the exponential and turn it into a log. You're also going to start at the b, always start at the b, loop to the other side, and then come back. So you would have to start by writing the word log, make the b into the little base of y equals x. Hopefully that will make a lot more sense once we see a bunch of them below. But again, I'm going to use the loop rule to try to help you learn how to go back and forth. So first, we are going to go ahead and take each of these log equations and turn them into an exponential equation. You know that these are all log equations because of the fact that they all have the log in them. And if we're going to go ahead and utilize the loop rule, if you take a look here at the ones that are already done for you, if you start at the 2, loop to the 4, and then come back, you would say 2 to the 4th equals 16. Here, for example, 2, start at the 4, loop to the other side, and then come back. 4 to the 0 equals 1. A very important note here. Whatever you write as your exponential, it has to be a true statement. Is 2 to the 4th equal to 16? Yeah. Is 4 to the 0 equal 1? Yes. You want to make sure that you're only writing a true statement, or else you know that you're screwing it up somehow. So let's go ahead and take a look here at number 1. So here in number 1, start at the b, raise to the other side, and then come back. So 12 to the first is equal to 12. Very carefully here, 1/4 to the -1 is equal to 4. And if you're wondering why I'm using parentheses, you don't have to, but we tend to want to do that when there are fractions involved. And then look, it gets faster and easier the more you do. 6 to the 3rd equals 216. 7 to the 0 equals 1. And again, each of those values should be a true statement. So this would probably be a good time to pause and try it. So go ahead and pause for a second. See if you can do 5, 6, 7, and 8. And then we'll go ahead and go through them together. So if you had a chance to pause and try it, 21 to the first is 21. 1/5, which again, we tend to use parentheses, to the -1 is 5. Maybe you don't even have to draw the loop anymore. 3 to the 4th is 81. 14 to the 0 is 1. So that is your first goal for today, to be able to take something with a log and be able to rewrite it as an exponential. Now, as much fun as that was, we now need to be able to go in reverse. So you have to be able to take an exponential and be able to rewrite it as a log. So the first step in all of these problems is to write a log, L-O-G. Couple of things you might want to remind yourself of as we go ahead and do these problems. You hopefully want to remind yourself that the square root of x is, of course, equivalent to x to the 1/2 power. Further, the cube root of x is equal to x to the 1/3 power. And again, same for fourth roots and fifth roots. You also want to remember that x to the -1, remember that that is equivalent to 1 over x. And if you can kind of remember these exponent rules from chapter 5, it just helps to kind of make a little bit more sense in terms of why the statements are all true. Again, each of these exponential statements are true, and these green rules are why. And now we're going to write equivalent log statements that are true, although you don't really know enough about logs yet to be sure that they're true, but it's a good start. So take a look again at the ones that are already done for you, example 1 and example 2. These are also using the loop rule. You just have to make sure you're starting the loop in the right spot. So you're going to start the loop at the base, to the other side, and then back. So start by writing the word log. Then you started at the 5, you went to the 25, equals 2. Over here for example 2, again, start by writing the word log. Start with the base of 10, to the other side, equals -1. Now, I promise you that each of those log statements are 100% true. You might not know that yet, but your goal, as always, is to write a true statement. So here for number 1, again, if you're going to go ahead and think of it as a loop, the first thing you're going to do is write the word log. Then the 8 is the small base, so you draw that as a subscript. Full size 4 equals 2/3. Over here for number 2, again, draw the loop. Start with an log. Base 6, which is a small number. 1 over 216, which is a full size number, equal to -3. And again, think about why that exponential statement is true. If you did 6 to the -3, that's really 1 over 6 cubed, which is why it's 1 over 216. Here for number 3, start with a big log, then a small 8, regular size 64 equals 2. And one more time, log base 20 of 0.05 is equal to -1. And I just want to really caution you here, make sure that when you are doing this, you are writing things in the appropriate font where they should be. So basically the base of the log should be a small subscript, and then everything else should be full size in a line. You want to make it clear, again, that everybody is in a nice regular line, and then it's just the base that is a subscript. So again, this is probably a good place for you to pause and try it. So go ahead and try 5 through 8, and then we'll come back and go through them together. All right, so if you've had a chance to try, you would say that log base 50 of 1 is equal to 0. Again, maybe you don't have to write the loop anymore. Log base 16 of 8 is equal to 3/4. Log base 3 of 27 equals 3. And finally, log base 15 of 1 over 225 is equal to -2. And again, once you get the relationship part down, the loop rule, just make sure you're writing stuff in the correct font size, exactly where it's supposed to go. Now that you understand how to go back and forth from a log to an exponential and vice versa, you might be asked to evaluate some logs. And in order to evaluate some logs, you really just have to remember your exponent rules. So there are actually 2 special logarithms that you should always be aware of, and you should always be able to calculate without a calculator. And that's if you're taking the log of 1, or if you're taking logarithm base b of the same base. So here, log base b of 1 is always, always, always equal to 0, because b to the 0 equals 1. And again, that relationship is just the loop rule. So an example of that, if I was to evaluate log base 6 of 1, because of this 1, doesn't matter what the base is, once I see that 1, that's how I know that the answer has to be 0. Over here on the right, if you're being asked to evaluate log base b of itself, that is always, always going to be equal to 1, because b to the 1 is equal to b. And again, that's the loop rule. Here's an example. If you were asked to find log base 8 of 8, Doesn't actually matter what the numbers are, but as long as they are the same, that's how you know that it's always going to be equal to 1. So those are kind of the simplest, easiest logs for you to find without a calculator. And now let's go ahead and turn to the next page and do some others. So again, I'm going to call this evaluating log expressions. And you should be able to do these without a calculator. So consider log base 4 of 64. The question you're asking yourself when you're trying to find log base 4 of 64 is what power of 4 gives you 64? So basically, 4 to what value is equal to 64? Well, based on all the exponent problems we've done in the last couple of weeks, hopefully you'd be able to find out that that answer was 3. Now, again, if we're asking you to do these without a calculator, they're only going to be integers or familiar things. If the answer was 2.7583, there'd be no way for you to find that without a calculator. So keep that in mind as we try the next set here. So log base 5 of 125. The question that this is actually asking you is they're saying there is some number that this is equal to, let's call it x. Using the loop rule, this is asking you 5 to what power x is equal to 125. Well, you can use your you can use your cheat sheet from chapter 5, or again, you should try to do it without a calculator, but obviously we can't stop you. So 5 to what power is equal to 125? Hopefully you'd be able to relatively easily find out that that is 3. Take a look here at number 2. Again, log base 4 of 4. You're essentially saying to yourself, okay, that's equal to something x. And then the question that you're answering is 4 to what power is equal to 4? Well, that was one of our rules from the previous side. The only way you can have 4 to the something equaling 4 is if it's just equal to the first power. Here in number 3, again, let's say that it's equal to some value x. So 2 to some power is equal to 32. You would want to try to find what that exponent is. And again, that would give you an answer of 5. So here's the bottom line. When you are evaluating or solving for a log, really all you're finding is an exponent. Log base 5 of 125, the answer to that question is what exponent is 5 raised to that gives you 125. So really, evaluating a log is much simpler than it seems. And again, as you get better and better at these, maybe you don't have to write the x part. Maybe you can just do it in your head, but continue to do it as long as it's helpful. So here in number 4, you're essentially saying 2 to what power would give you a half. So this is really 2 to the x equals 1 over 2. So how would a 2 stay a 2? Well, that would only happen if the power was 1. But then how would the 2 wind up in the denominator? That only happens if there's a negative exponent. So that's how I know that it's a negative 1. Similar scenario here in number 5. 2 to the what is equal to 1/4. Well, how does a 2 become a 4? You would have to square it. How does it wind up in the denominator? It would have to be negative. 6 to the what is equal to 1. The only value that is ever going to be an exponent that gives you something of 1 is always going to be 0. And again, that is something that we saw on the previous side. And again, as you get better at these, it's possible you might not have to show any work, and that's fine. So log base 2 of 16, again, if you want to try to do it without writing anything, you're asking yourself, 2 to what power is 16? It's the power of 4. Log base 3 of 81, 3 to what power is 81? That's also the power of 4. And then 3 to what power gives you a 9th? Well, how does a 3 become a 9? You have to square it. How would it wind up in a denominator? It would have to be a negative. So again, these are only the first logs that you're being asked to find without a calculator. So hopefully it makes sense. And again, you'll get a chance to practice quite a few more on the homework. And then what we want to talk about next is this idea of a common logarithm versus a natural logarithm. And again, because you're just getting started, that might not make a ton of sense, but you're going to want to go ahead and at least think about it. So when they're talking about a common logarithm for everyone is known to be a base of 10. That is just the standard base that everybody starts with, again, called the common log. So you're more likely to see the right-hand side, log of x or log of 3. What you basically have to know is that that is really log base 10 of x and log base 10 of 3. When they're talking about the natural log has a base e, and remember that e is the irrational value we talked about in section 6.2. You're more likely to see it as the ln of something, so the ln of x or the ln of 8. What you have to realize is that when you see that ln, they're really seeing that it's log base e and log base e. So this is worth knowing because even though you're going to see the right-hand side, your brain kind of has to think the left-hand side, and similarly over here. There's so much more to come with that as the lessons progress, but really all I want you to be able to do right now is I want you to be able to evaluate these common logs and these natural logs in your calculator to find the value of them. So again, all the problems we did so far, we wanted you to try to do those without a calculator, but now for this next set, you don't have any other option. So notice it says use a calculator to find the value of each log or natural log, and you're going to go ahead and round to exactly 2 decimal places. So I'm going to show you how to do this on my calculator, and then you can go ahead and follow along. So as I pull up my calculator here, notice I'm on the home screen. The log of 21, the log button is located on the left-hand side near the bottom half. And if you go ahead and press it, it automatically opens a parentheses for you. So you're going to want to just make sure that you close it. They're asking you to find the log of 21. Go ahead and close the parentheses. Your calculator is smart enough to know that that is the common log, so it's base 10. So if you go ahead and say the log of 21, it's going to give you the answer. You're going to go ahead and write on your paper, rounded to 2 decimal places, so 1.32. Then they want you to find the natural log. The natural log is an ln button, which is directly underneath the log button. So again, if you press the ln, it's going to open a parentheses for you. You're going to type in -3, and again, make sure you choose the negative button and not the minus sign. Close the parentheses. Ooh, unfortunately, it tells you that that is a non-real answer. As far as we're concerned, that's going to be a no solution. So you're going to go ahead and say no solution. It's an error. We'll talk about why in a minute. Then you want to find the log of 4, so 0.60. Then you want to find the ln of 7, 1.95. And then you want to find the log of -2. And maybe you think that you know what's going to happen. You can see again, it tells you that it's a non-real answer. So as far as we're concerned, that is another no solution. So just to kind of take all those answers and put them onto my screen here, the log of 21, that is equal to 1.32. The ln of -3, remember that is a no solution. And similarly for the log of -2, then 0.60 and 1.95. And there's a couple of conclusions that we can actually deduce from this. So before we get to that, underneath, I just want to show you here, what is it that the question you're actually answering? Here in number 1, because it's a common log, you're really saying 10 to what power is equal to 21. Here in number 3, you're really saying 10 to what power is equal to 4. And here in number 4, you're really saying e to what power is equal to 7. So those are the questions that you're answering. And again, those are not things you should be able to do without a calculator, which is why you're not being asked to do so. And then finally, if we take a look at what happened here in the pink, something that is going to be true now and forever is that there are some rules about logarithms. So you're going to want to go ahead and write the following. You are not allowed to take the log of the following. So no log or natural log of 0 or any negative. If at any point you try to find the log of -3 or the ln of 0 or the log of -15, there is no way that you'll be able to do that. So you just have to make sure that you understand that you can never take the log or the natural log of 0 or any negative. That has big applications for graphing and for solving, which is what we're going to talk about next time. So thanks very much for tuning in, guys, and we will catch you next time.